Swayam Prabha. Digital India. Educated India.
Okay, goes by pretty quick. So we have a lot of different topics today. I mean, I put a few things, but again, a lot nice concepts, there's some analytical work, things of that nature that we'll present. Because we saw that the analysis varies from basic to all the way complex, and we'll cover all the spectrum, including what you have done calculations wise. Those are numerical. So the differentiation between analytical, numerical, and advanced also is numerical, finite elements, but mid numerical and advanced numerical, hand calculations numerical versus advanced numerical. So all of that we will get exposed, and today we'll look at some analytical information as well. So main topics that I planned today is the influence of rise time, and I thought I had one graphic, but I don't seem to have that. Then we'll take up an example, and then we'll get into pressure impulse, or it's known as pressure impulse concepts and diagram. And also these are, I'd say, not energy, but you can say sort of the Rayleigh-Ritz principles, impulse momentum Rayleigh-Ritz principles. And then time permitting, we will look into nonlinear material aspects. So the plan is, hopefully we get through a lot of the basics today, by today and Monday more first session. And then we'll spend a couple of days on the analysis aspects of it, of structures. How do you apply all of this to a real structure, elements? Then we'll cover the design aspects, the reverse. If you're given a certain loading, how do you come up with design? So the design principles of it. And then we'll look into advanced concepts like progressive collapse is something I want to spend at least a session or two, because gives you an idea of what you do irrespective of the loading. There are ways to just strengthen structures, design structures for that. And then there's a lot of questions that you have been asking, so I'm preparing some additional material. Was preparing some last night. I have some more, so depending on how the time goes, we'll address that later on. So that's sort of the plan. So what we have seen so far is did I talk about the elastic shock spectrum? I did, right? Yesterday, I did. Okay. So we've looked at the elastic shock spectrum. Let's now look at the influence of the rise time. Most of the principles we have seen had zero rise time, but the rise time also does play a important role in these analyses. And again, these are analytical expressions. I will show some graphical representations as well, and we'll upload the documents in the Google Classroom. So you have P naught versus T. The uh, influence of rise time is you have a rise and then perhaps you have a constant, or it could even be exponential. So let's start just with the simplest basic case. In the basic case, we had a constant P naught, and here you have TR, and this is TD. So this is the applied load. So when you are setting up the ordinary differential equation, you now have three components to it: x dot plus omega n square x, and you have seen that we need to break these things up. We've seen how to break it up. Now this is equal to P naught divided by TR multiplied by T. This is for 0 less than T less than or equal to TR. And then this is equal to P naught for TR less than T less than or equal to TD. And then finally, we have to set the last part up, because now you recognize that the response can be well after the load has passed as well. So it's important to set up a differential equation for that purpose. And if you solve this, the basic solution is you have your x is equal to delta static. This is T divided by TR minus sine of omega nt divided by omega ntr. This is for T less than or equal to TR. Now, it gets a little more complicated. This is equal to x of TR, that's the initial position at T equal to TR, cosine of omega n, again minus TR, plus the x dot of TR divided by omega n, sine of omega n T minus TR, plus delta st 1 minus cosine omega n T minus TR. So that is three components. This is for TR less than T less than or equal to TD. And we can assume TD is large, and there is also a component for T greater, but if we assume is large, this should be large, then we can ignore, or for now we'll skip the third part. Only under impulsive situations, and under impulsive situations you're likely to have the response within well beyond TD. So here we are assuming the response comes within here. So in situations like this, one thing to note is it is quite likely where your TR is of the same magnitude as the other TD itself. In this situation, the deformation response is likely maximum, and I'll just add that caveat, during the constant load phase. And we can write the delta dynamic is equal to delta static multiplied by 1 plus 1 by omega ntr multiplied by square root of 1 minus omega n minus cosine of omega n omega n tr square plus sine of omega n tr square. And if you look at the increase, R as equal to delta dynamic divided by delta static. So that is basically the expression in the brackets. You can simplify this as 1 plus sine of pi tr by tn divided by pi tr divided by tn. And we can, so we can look at this. There are, I don't know if I have this graph. I should have printed this. So you can plot R as a function of TR over TN. And what I'll say is, I'll see if I can put this graph. It's not very clear. Let's say your response is something like this. Let me plot a couple of them, at least the extremes. Now, or maybe 2 or 3 of them. If the response is something like this in all cases, again those graphs will be better. So between extremes of, if TR by TN equal to 0.2 versus TR by TN, let's say of 2. So your rise time is quite high. Then the response is likely to be more like this in this case, whereas here the response is likely to be more pronounced in this manner. And in between, if TR by TN equal to 1, which is, and here the response is more. So I'll give these types of, I have a graph that I'll upload in Google Classroom, but let's make a couple of notes that is helpful from all this. If TR by TN is less than a quarter, then the delta dynamic, this is the static response. The delta dynamic is likely to be twice delta static. This is a short rise time. Now, however, if, as you see, this is short rise time, whereas this is large rise time. So if TR by TN is greater than 3, then delta dynamic is approximately delta static. This is for long rise time. So in all this, why are we going through this? This is the story. Influence of rise time. Every story must have a nice conclusion, ending, right? Otherwise, no movie is good. So this is the influences if you have your short rise time, then, and we saw yesterday as a blanket thing. We just said that if your P naught is constant, right? If P naught is constant, then we said that delta static is delta 2 times, I mean delta dynamic is 2 delta static. But here you see the story a little bit different depending on the rise time that you have. Again, short rise times, that assumption is valid, and then you can actually plot if you would like on your own. Let me add a couple of things for you to, for those of you especially who are interested, try on your own. In this time frame, we cannot to plot and make observations. We cannot do everything, although it would be best if we could and then get more out of it. But you can see if you have the time, put into it and see, you can plot and give some numbers and see how that thing goes. So any questions? So the general story is likely to be this, but of course it won't be 2 times delta static. Then you're now looking at the elastic shock spectrum, right? Those values are lesser. So you're probably looking more up to 1.5, 1.6. Whereas the main story, if your rise time is very high, even in a triangular load, like if you have a up and down phase, then you're likely to be more in the second scenario. And why is this, which application would this be? Some of the blast wall loads you saw, right? You plotted a bunch of those graphs. So an application would be, there are several applications. One application would be, draw the P versus T for walls and decide on deflection calculations based on this principle. Many petrochemicals facilities, if you're working in that area, so you've seen something like this in many scenarios, or you have seen petrochemical facilities, there'll be more like this. Sort of, it does have a rise time, and the rise is not linear. So in all these cases, depending on, that's your TR, this is your TR. So depending on that, you can judge. At the end of the day, many of these are not direct answers. It's not a PL cube by 48 EI. You're never going to be accurate in these cases. Judgment plays a big role in all of this. Okay, now another concept I thought I'll present. I talked about it yesterday, but wanted to present the idea a little bit more in detail. Is we've seen what an impulsive load is, but the influence of the impulse loading response. Now, what is an impulse? It's nothing but if you have a pressure wave, something like this, you can consider the impulse is nothing but a short P, let's say this is P naught and TD. So your impulse is P naught TD. Now, let's consider two scenarios. One, TD is very short. Basically, you don't have a triangular loading. The TD is basically right here. This is, let's say, P, this is P naught. And secondly, the rise time is much lesser than Tn. So, you do have a impulsive response. Now, if you look at the differential equations or the ODE, in this case, you have x double dot plus mx dot is equal to P naught for 0 less than T less than or equal to TD, and this is equal to 0 for T greater than TD. So, these are the two, and you have initial conditions. It's an initial value problem. So, the initial conditions are 1 x of t equal to 0 and secondly x dot at t equal to 0 equal to 0. So, I want to introduce the concept of, there are two principles. One is kinetic energy and the energy principles, and the other is what is, you've all read at some point, impulse dash principle. So, the first one is work done energy principles, the second impulse dash momentum, right. So, impulse momentum, they both go together. So, using impulse momentum principles, now I is equal to mv. So, therefore, V is equal to I over m, which is, now I here is P naught multiplied by T. It's, remember, it's a very short, we have given those things. This is P naught multiplied by TD divided by m. So, this is the velocity at t equal to 0 or at t equal to TD, but again those are very small. So, if we assume that since t equal to TD is very small, we assume that the momentum is applied and instantly it becomes the velocity. So, when we solve the differential equations, we have here x again is equal to a cosine omega nt plus b sine omega nt, and x dot is equal to minus a omega n sine omega nt plus b omega n cosine omega nt. So, you have these two. So, solving and applying these two, so you have this condition applied and this condition applied. So, this is IC1, let us say this is IC2. Again, we are understanding the principles out here. What you get is x is applying the ICs. Now, especially let me show you the second one. The first one, so you apply, for example, at x dot, is equal to B at t equal to 0, x dot is equal to B omega n multiplied by 1 is equal to I by m. P naught by t is I by m. So, from here you get B is equal to I divided by omega n m. And applying the first principle, A goes to 0. So, at x of t equal to 0 gives A equal to 0. So, this gives you a very nice expression. Again, the power of analytics. I mean, nowadays everybody talks of analytics, right? In any decision making process. Analytics has come in through data. Here, this is through analytics, nothing. And we are understanding analytics from, look at the irony of it. Here, everything analytics is data driven. In our case, analytics is driven from first principle, science, right? And so other situations, you have to learn to simplify these things. Whatever the purpose, one of the objectives here also is to expose you to scenarios where you might encounter and you have a question, then how do you simplify it to, and we have presented principles. Constant P naught is always a great starting point. I'm going to use that in a couple of other examples. So, what you get is x equal to I by m omega n sine omega n t. Now, in blast loading, again, we are not going to solve this, but presenting the idea. In blast loading, let's say we go to a triangular approximation. So, this is your P naught, P versus T. You can think of two different things. So, here if you see, there are two time variables. Now, let's say you are analyzing here. This is dt. And this curve is P naught multiplied by 1. So, one of the time variables here is t. So, this is, if you are integrating for area, you would say t dt and go about it. But the total di, the di, if you see, what is di in this case? It is just a di. This is for this part alone. 1 minus, right. Now, so that is di. But when you are looking at the x response, dx for that part is di by, let's bring this into the picture. So, di m, take a simple derivative, di by m. Now, I am not taking a derivative, it is just a small, the response let us say is dx, I omega n sine omega n t. Now, when I take the integral to find my response, what is the response dependent on? Yeah, little, what did you say? The rise time, but here we are not looking at the rise time. But here if I see in this graph, let us look at this graph alone, and what would be the response dependent on? P naught, And all other, like this, there are many, right? All these impulses add up. So impulses up to that point. So there are two time variables. You have to find the integral of the impulse, right? So need the integral of the impulse, and then up to that point. So this is your second, let's say t1, the second time variable. And the di itself for that is p naught 1 minus t over td. So you will have this as, let's say, t1, to find that impulse up to, leading up to that point, to add, and then, so all this comes to x is equal to from 0 to t tau dx. So which is basically 1 by m omega n integral 0 to t p of tau. Again, sine, here let's put tau d tau. So this is what is known as a convolution integral. And yesterday I talked about, you solve the convolution integral using Duhamel's. Again, we won't get into it, but again, just a exposure of it is, that's why we go always to a simple P naught constant case where you don't need to get into these. There are solutions again, analytical solutions for Duhamel's integral, and so let me, yeah, I don't know if it is necessary. This is a general form of Duhamel's integral where you have a function of tau, two functions. So the two time variables, it's a product of time variable 1 and time variable 2. Tau instead of t1, let's call that tau. So two time variables, you take a product dt going from 0 to, sorry, this is dt, going from 0 to t, going from here to here, and then of course all the way you go up to td. So these are some more complexities that you get into, and if you are interested in numerically, so when you look at some of the codes, nonlinear and other such things, how do they develop? They go through these principles, apply numerical integration techniques instead of analytical expression techniques, and then if you're interested, you can, it's all fascinating stuff, but work has been done already. So many of it is readily available. Any questions so far? So that's where the shock spectrum, let me push this again, import file. I showed a little bit, we've seen that yesterday. So the shock spectrum development for various kinds of curves you can come up with using these types of principles. So let's take an example. Let me put that shock spectrum anyway. I think we may still have it here. So it is there. So at least we have that part. Well, let me see if that shock spectrum showed up. I think it is there. It's just not visible in that. Yeah, you see it is here. Oh, open this again. Oh no, that was yesterday's. So browse. I think we didn't save today's. Huh? We may not have, I think. Well, at least we've stored it. So this is day 4. Browse. Yeah, I don't.
Below that.
Oh, this one, right? Yeah. Okay. Good. Good. Okay. Yeah. So let's take a simple example. This is an SDOF type analysis where you have a structure, a steel structure in particular. And I know many of you or all of you are not familiar with the units. The best thing I would suggest is to, especially if you're using FPS units, select a set of units and multiply and keep consistent with that. So either you can use kips, inches and second, or pound, inches and second. So when you convert it, use for analysis, we are calculating static deflections, then feet is a better unit, and then convert feet to inches for further analysis. So hopefully now you're multiplying and then numbers will look good and you won't be spending. Understanding the significance might take a little while, or you can apply them to your own problem. I'm trying to bring you, okay, I think I found the UFC 34002 figures in SI units, KPA. So the same exact figures, the Kingery-Bulmash expressions for figures 27 and 215. So we'll share that also. I actually looked at it, I found it this morning. So the height here is 12 feet. And this is rigid. It's given that the weight of the floor is equal to 8.5 kips. The two columns, these are oriented in this manner. The two columns are what is called as W24 by 85, again 24 2 feet deep and 85 pounds per foot. What would be an equivalent one? Here, anybody does steel? Something 200. 12 is 300, so 600 millimeters, right? Deep, something 600 by. Anyway, I was just curious. And the moment of inertia is 1350 inches per 4. And the modulus is, steel is what, 210 gigapascals? What's that? 210 gigapascals, right? So if you are to get an idea of that. So question is, for PR equal to and 20 psi, TD equal to 20 milliseconds, TD equal to 60 milliseconds. Find the elastic dynamic displacement. The screen, this Wacom tablet is really nice. I'm tempted to now go back and order this, but it's hard to carry around. You have to fix it in one. Smaller version is good, yeah. So let's start with, it's a triangular load. Triangular pulse. First step is the data and the dynamic structural properties. So you have static structural properties such as inertia, area, length, but its dynamic footprint or dynamic structural properties. This is structural, not static. I'm saying the word static, I think. So dynamic structural properties. Mass is W by G, and for those of you who are not familiar with it, in 9.8 meters per second square is 386.4 actually, you can use 386. So this is here, we saw the effect of mass inclusion yesterday. So keep that in mind. What do you want to include for your mass? It doesn't go into stiffness. So W slab plus W of the columns divided by G. It's also given that the data is floor weight is 8.5 kips. And clearly you can include the floor weight. Wall is something you have to decide only if it is integral and it is acting with the system. So going through this, you have the slab is 8,500 pounds plus you have two columns, 2 times it is a W 24 by, sorry, this is 55. So 2 times 55 pounds per foot multiplied by 12 feet. So divided by, now, so all you have is pounds here, get 386.4 inches per second square. So the unit is called a slug, but I don't ever, first of all, slug, have you seen a worm slug? Do you know that it's a worm? Yeah, doesn't look very good. So that word itself gives me a yuck. So 25 pound second square per inch. And K is, in this case, 3EI by L cubed, because it's PL cubed by 3EI. So 3 times 30,000 KSI, kips. So this is 1350. There are 2 columns divided by length is 12. So the stiffness value 81.3. And so omega n is square root of K by M, being consistent with the units. 81.3 multiplied by 1000 divided by 25.1. Many times my students in class complain I write too fast. Am I writing too fast, or it's okay? Okay. And then the natural time period, omega n divided by, sorry, the other way around. 2 pi by omega n. And so this is 0.11 or 110. So notice numbers also. Structures, single story structures are in the range of 50 to 100 to 100 to 200 milliseconds, and this is a significant amount of load. Yesterday also we saw a couple of examples. You can simplify multi-story structures if you're working with non-structural buildings, non-structural building components subjected. Again, you can convert that to an equivalent system like this and be able to perform analysis. So, the next step is to calculate the load on the structure and the static deflection. So, we are looking at the SDOF system like this. So, the SDOF identified is, this is the deflection at the top. Let's assume that these columns are, or these frames are so this is 20 feet center to center. You might, some people might say, I'll take half the load. So let's say this is the blast, this is 12 feet. So this bottom 6 goes to the base, the top part of it. So this could be the tributary width. Or so those are again judgments you make. So what you have here is P naught is 20 psi. Is that the, what is the 20 psi? So P naught is 20 psi multiplied by 1/2 multiplied by 6 multiplied by 6 feet 12 inches multiplied by 20 multiplied by, so convert that to inches. So P naught comes to 375. Hopefully my calculations is correct. In all my classes there's usually one person who's running the calculator, finding out any error that which is good. At least he or she keeps engaged during the class. And some figuring it out who that person is in this group. Height. I took half the height. Yeah. So delta static is now P naught divided by K, which is 375.6 divided by what was K, 81.3 kips per inch. So this is 4.24 inches. Then the third step is, this is actually an easy process to calculate the dynamic deflection. This is from the elastic shock spectrum. That we just imported. Why did I take which one? Oh, this tributary width. Oh, the other half goes at the bottom. Or you can take full also. If you want, if you have put your structure in a way that you're supported it, even if you have a floor beam, right, going across, that beam will probably send the loads to the base. No, the wall is, you will have walls, right? Yeah. So maybe I should have mentioned that. You will have walls between frames spaced 20 feet apart. And so we look at TD for TD equal to 20 milliseconds. TD by Tn is 20 ms divided by 110 milliseconds. So this is 0.19, and surprisingly this process is so straightforward. So 0.19 impulse duration to natural time period, so that's roughly right here, and going up to the first curve here, and we come, so roughly 0.46.65 or something like that. So here if you notice, so you get delta dynamic by delta static equal to 0.65 from, or 0.7 from the ESS. Let's call this ESS. So delta dynamic is actually lesser than, I don't know how much this is, 60% of 42. So the wall in most cases, even in seismic analysis, if you go, the wall is considered a mass, but it provides stiffness only if the blast load is in the direction of the wall. Not here, the blast load is perpendicular to the direction of the wall. So the stiffness it provides is considered, you can neglect it. And it's a very fair, very reasonable assumption. 20 feet center to center, yes. Because see, the pressure load is coming, this is the wall and this is a column in between, right? So the pressure load that is coming, it is resisted by the column. So the frame is taking the pressure load there, only half the height. So what is this number? 0.65 times 4.24. 2.77. And kind of sounds counterintuitive, but then it is a very short duration. But if you look at now TD equal to 60 milliseconds. So now TD by Tn is 60 by 110. So this is 0.54. Yeah, right. It should be. So the spectrum, that's what, if you look at the spectrum, up to a certain uh, impulse duration. And yesterday, remember, we saw those equations, right? Those equations, these are elastic behavior. So while we say it is delta dynamic, it hasn't had the time to go past static. That's what it means here. So even though you're giving an impulse, that impulse is not sufficient. It's like you're trying to jump, but I'm not done enough impulse to jump. For me to jump, I have to give more impulse. So it's in the lower phase. Second one is Td by Tn is 0.54. So that's somewhere, let's say here. And well, actually, probably not that. It'll be, I don't know what I'm doing. So 0.54 going to the triangular somewhere here. And let's say 1.3 or 1.25, whatever you want to pick. So R is equal to 1.25. Again, help me with this. Delta dynamic is 1.25 multiplied by 4 point, how much was it? 2.4. 5 point. And for maximum response, how much duration would you need? Let's just look at that. So the maximum response in this case is somewhere, it's plateauing somewhere here. So let's say this is 1.7. And if that's 1.7, you're looking at almost this coming down, Td by Tn of 1.8. So for maximum response, R is equal to 1.7, Td by Tn is 1.8. So Td is equal to 1.8 multiplied by 110, that is 180, 198. So given all these various ways to establish how much protection that system has, looking at the levels of protections, all those I've showed. I think this 5911 we'll get into what are all the different levels of protection. We've seen that, but we'll look at it in more detail as we go along. So general comments, again, after a movie, what do you do when you come out? Huh? What do you do? Review. This was good, that was not good, right? Who doesn't do that? Postmortem or so let's, after watching this movie, now you review. So what would you say as stiffness goes up? Think about it. This is just a moment to reflect. Say, for a given TD, small TD, TD by Tn So, just an exercise. What happens to omega n as stiffness goes up? Okay. Stiffness goes up, omega n increases. So, let that settle in. And then what happens to Tn? So, what is important for us? We don't quite design with omega n, right? We're thinking of natural time periods. So, anytime you want to mitigate some things, the ratio that is important to, which ratio is the most important ratio so far we have seen, at least today? Td by Tn. Of course, there's another variable also, that's why I put given. So, so Td by Tn, what happens to it? Td by Tn tends to goes up. And delta dynamic also kind of, isn't it a little strange? Right? What happens under normal cases if your stiffness goes up? Deflection. So, isn't that kind of strange a little bit? Think about it. I mean, these are, again, we keep looking at it. Why is it important to go beyond, always go beyond numbers? And if it's telling you a new story, see and accept stories that are different from the standard, same movie, same actors, same songs, you go back, no. So, analyze and see if it makes sense. You have to decide. There's nobody who's going to help you decide but yourself and maybe your colleagues. So, that's the stiffness effect. Second is mass effect. Wn Tn Td by Tn. What happens to mass? Omega decreases. Tn goes up. Td by Tn goes down. Delta dynamic, it decreases, right? See, this is significant. Remember, that's why we talked about mass being a very important aspect. But at the same time, stiffness is also too. Reducing stiffness does help too. So, you have to make those adjustments when you're actually designing structures to resist blast. It is how do you, what would you have to pay attention between, if you were designing to include that wall with the column? When you're designing, you're sending out some drawings, what's the attention you would focus on now? So, you're looking at a shape, but let's say the shape is still the same, it's a building and moment of inertia, but that how to orient, well, that is one thing, but in terms of the wall and the column, what connection, right? You have to really see how well connected is the mass. What if the wall just blows out and you've designed using this principle? Well, is it applicable? No. Now, so the connection costs in blast design can be so prohibitive. Let that sink in. Let's say this is not planned, but let's just see. Let's say, and this is pretty quick, it can happen. Let's say in the wall blows out. In a blast, but not the column. So how does it, question is, how does it affect? So this, as they say, is out of syllabus, not in my notes. Affect the column. What do you think? We don't need to get quantitative numbers. Just look at this chart of this sets of red and black arrows, and so clearly mass is going down, right? So your delta dynamic is going to go up, down. Let's look at a number also. Mass goes down, so therefore your delta dynamic goes up. So it makes it even worse. Now let's quickly look at the omega n is square root of the stiffness still remains the same. So omega is mass is 2 times 55 times 12. So now the mass is 2 times 55 times 12 divided by 386. How much is this? And omega is square root of k, which is 56.55. Times 1000. Wait, k is 81.3, sorry. So 81.3 times 1000. How much was this number? 3.42. How much is this? $154 point for the first case, omega n, and Tn 40. What was it before? 110. So now, see, we're going to answer your question. How fortuitous, coincidental. So now, therefore, Td by Tn, and let's say Td is equal to, what was the second number we looked at? 50 milliseconds or 60? So Td is equal to 60 milliseconds. So this is 60. I think I was expecting a question, so we went with this. Not really. So this is 1.5. So to answer Raghav's question, if we go 1.5 here, going all the way somewhere, let's say 1.5. So now And so when you're presenting, so this is 1.68, let's say. So your delta dynamic is R times delta static. R is equal to 1.68 from the elastic shock spectrum. So this is 1.68 multiplied by 4.24. How much is that? How much? 4.24, right? How much is this? So what will you have in your report? Brief delta static is 4.24. Delta dynamic is, how much was it? 5.3. See, it's a simple problem, but so many things out of it. With wall, delta dynamic is 7.12 with blowout of wall. And what you can do is, you can also say LOP category. For this case, expected level of protection category. Now, how will the levels of protection be? So, for example, so this is steel. So, although you have a concrete, but the primary structural element that is resisting is steel. You have a wall, but none of those are resisting. The resistance is provided by steel. So what do you do is, we know it's going to deform like this. And if this is your delta, this is L, we take a triangular. So for ductility demand, mu is delta over L. So which is, what are these two values? 5.3 inches by 12 times 12 inches, or 7.12 inches by, help me with these numbers, or support rotation. No. This is support rotation, sorry. So this is theta, because tan theta is approximately, theta is delta by L. So this is your support rotation. And ductility, any numbers on this? How much? Radians. So if you convert to degrees, 0.1 degree, 2.1, and Now, if you want to see, just let's say you don't have too much other information and you want to get a gauge. Okay, is this too much, right? Is it too little? You know it's going 5.83, that's a lot. You know, a 100-story building, how much does it deflect under wind? How much at the top? Design deflection. Not, so under peak wind, it can go, a 100-story building is how many feet tall? Let's say each story is 12 feet. So, 100-story building is 1200 feet tall. So, just if you're not, again, forget the units, how much do you think it can go either way? With safely, you're sitting on top, peak wind, and you are swaying. 10, yeah, closer 6-8 feet. 6 to 8 feet, you can go either way. That's a significant number. So the numbers don't just so you're not feeling good. That's not the structural designer's problem. It's the owner's problem and your problem that you're there. But the owner said, I can afford only so much. And otherwise, if he wants to have 3 feet, then the structure is 4 times the size or whatever. So how would you, can you give me a metric you would gauge saying, that's too much, it's okay, this. Again, this may be more civil engineering people. You may have seen this in mechanical engineering. You have limits like this, but given civil engineering limits. What's that? 500? So H by 500, 300, 500, something in that range. So what is H by 500 here? So under wind or seismic, as they call the drift ratio is, he said H by 500, I say H by 300. I think, I don't know, maybe Indian codes is 500. We commonly use 300. So this is 12 feet. How much is this? Clearly less than 1. 0.48 or 0.5. So clearly we are way over in a scenario like this. But then when we, I don't know if I've already, let me see if there is. I know I did show we'll come to that. Hold this thought. These are some, okay, let me see. These are burst, survival, reflection coefficients. Maybe it is day 1. The ASCE 5911, for example, that I mentioned, or 5922, the documents like that, they have the limits on. I'll bring that number to see if this is. So from here, we'll stop with. So from here, we decide the level of protection. So you can go back and say that the level of protection has dropped from, or it went up from medium to low. So that's why it's dropped. It's gone down if there is a blast wall blowout. So those are assessments that are made. And what I'm showing, it's not very complex, right? Calculations are simple, but there's a lot to taken from this. And these are, I would say, if you're doing routine, some designs, these are design calculations you can directly use, steps. to come up with decision making. So just because we think an explosive is a complex event doesn't mean we have to use the most complex analysis to get, because the complex analysis is not going to, can ask people who have done, several of people here, students have worked on any of these stories. It won't even end, right? You use your element methods to do analysis, and out of a structure it is, you have got to dig through post-processing and do stuff. Nice, interesting material that we'll go through.